Hello everyone, this is Jack from the PyTorch XLA team in Google. Today I want to continue my series and talk about the PyTorch XLA data parallel with the SPMD. So let's get started. Let's first recap what SPMD does. If you haven't, please take a look at my previous video. And then we will talk about what is data parallel. I assume you have some prior knowledge, but I will still go into some basic concepts. Lastly, we will talk about how to use data parallel and SPMD, and then I will show you a collab that you can also run yourself. So this slide I actually copied from my previous slide for GSPMD. So GSPMD is a mechanism to allow user to only express their sharding intention, and then compiler will shard the tensor for the user. The advantage was user don't need to manually inject collective like OR gather and OR reduce. So here is a basic idea. So there are two important concepts in the GSPMD. One is called mesh, one is called partition spec. Mesh will describe how the device looks like, and partition spec will describe how a mesh can be mapped to a tensor. So for example, let's say we have 4 devices, and then we have a 4x1 mesh. The first dimension called data and second dimension called model. What it means is like so in the data dimension there are 4 devices, and then in the model dimension there's only 1 device. So this partition spec is a 2D partition spec. So you can only use this partition spec on any 2D tensor. So what it does is like it says like the 0 dimension of the tensor mapped to the data dimension, and the first dimension of the model mapped to of the tensor mapped to the model dimension. Since the data dimension you have 4 devices and model dimension you only have 1, this pretty much means you are going to shard the tensor in the 0th dimension by 4. Here's a similar example by flip the model and data. So now like you are going to shard the 0th dimension one way, which pretty much means replicated, but on the first dimension you will shard it 4 ways. Like there are other ways to construct a mesh, like you can make it 2x2, and then you also can just construct like the 1D mesh, and then like you can put the first dimension to be null in a partition spec, which means it will be replicated. It's essentially the same. The sharding one way and replicated is the same idea. So let's do SPMD. Before we dive into the data parallel, let's talk about how a single device training usually works. So there are 2 things you know prior to the training. The first thing is the data. So in the image model, like ResNet, like data are just image. For the language model, like the data are usually just a bunch of text. Let's ignore embedding for now. So the model weights, it's the model parameter. So both of them you know ahead of time. So in a single device training, what you do is that you let data flow through of the model weights, and then you got activation, and then eventually you can calculate the loss. From the loss, you can calculate the backward path of the step, and then you will get a gradient. Gradient is usually the same size of the model weight. If all of the model weights are like the request grad is equal to true. And then you apply the optimizer using a gradient which will update the model weights. And then you repeat this process over and over. So this one forward, backward, and the optimizer, we usually call it one training step. Then within a training epoch, there will be many steps. So what is data parallel? So as the name suggested, it's trying to do the parallelism like in the data. So first, let's take a step back. Like, why do we need the data parallelism? The first obvious reason is if you have more than one device, whether it's CPU or GPU, you want to utilize like all of the device. And second reason was like when you try to increase the size of the data, although it doesn't increase the size of the loss or the size of the gradient, it will increase the size of the activation, which is kind of hidden in here. So it will eventually alter memory. But if you can distribute the data across multiple devices, it's actually going to scale pretty good, as long as like your model weight can fit in a single device. So how does it work? So let's assume you have X device, and then each device like they get different data from data 1, data 2 to data X. all of the device, like all of the model parameter is in the device and it's the same, so you can say it's replicated. And then when data flows through, each device will get different loss and different gradient. The shape of the gradient is full. It means like the shape of gradient is actually match the shape of full parameter weight, but it's not complete because like this gradient only corresponding to this data here, but we actually have multiple different data. So what we usually do here is that we apply or reduce, usually reduce sum, which means we sums up like all of the gradient across like all of the device. So pretty much after this or reduce, like the gradient in all of the device will be the same. And then we apply the optimizer to update the weight of the model. And then because gradient is the same and the model weights are the same, so after the optimizer, the new model weights is also going to be the same. So then you can repeat this process over and over. So data parallel is very useful if your model weights can fit into a single device. Now let's take a look and see like how SPMD can be used in the data parallel. So first, what we need to identify is like, so in SPMD, that's one important concept is if you do not short this tensor will be replicated across all of the devices. So then if you look at like the previous diagram, that it's clear that the model weights is something we want to replicate it. So like obviously we're not going to short it, but data is something that we actually want to short across all of the device. Like that's all data parallel is about. So now in the SPMD scenario, so you get all of the data. So let's say for example, like in the previous like menu data parallel case, like the batch size is like per device batch size is 1. So we have totally like X data. Then in here, like you want all of the X data to be loaded in the process. And then in the data loader, like we will tell the compiler, here is the data and we want to short this data at the batch dimension. So let's say you have 4 devices, they usually want to short the data 4 ways, which is identical to the previous case, like where each device actually gets different data. So as here says, like data is being shorted at a batch dimension and the multiple weights is replicated. And the loss, as we discussed, is partial. It means like the shape of the loss is correct, but the value of it is not complete. Same for the gradient. So like each device, each physical device, like after the computation, it will have a gradient, and then compiler will actually insert the necessary corrective, which is most likely or reduce, to help you to reduce the gradient to the full value before apply the optimizer. So the beautiful thing about SPMD here is that all you need to do is to tell the compiler, I want to short the data at a batch dimension. And everything else, like the compiler will handle it for you. You don't need to spawn multiple processes, like you don't need to manually inject or reduce in the gradient. It's all being taken care of. So that's kind of a single host case, which like in TPU, within a single host, there can be like multiple devices. For example, on the TPU v48, so there'll be 4 devices per host. So there'll only be 1 process doing all of this. But what's going to happen if you have like multiple hosts? Let's say it's a v416. You have 2 hosts. Each host will have like 4 devices. So what happened? Well, it's actually almost the same. So in here, like in the data loading case, instead of say like in here, like the data batch dimension is 4, the batch dimension will be 8. So the batch, you will load more data into the host RAM. However, in this data loader plus mesh case, like the mesh, like here, compiler knows there will be total of 8 devices, for example. Let's assume like 4 accelerator like per host. And then compiler will do the right thing. Well, it's actually PyTorch XLA will do the right thing. It knows, like for example, this host only owns like the first half of the device, like the device 0, device 2, device 3, and device 4. So it knows that it shouldn't send all of the data to the device. It's only going to take the first half of the data, which I said here, data belong to host 1, and then it shot it forward and sent into the full physical accelerator in this host. And then starting here, everything is the same. Notice that here is somewhere the one thing that's not very optimized is like although we only need the first part of the data, we still load the full data like into the host RAM. So potentially here is something what we can optimize, but this is what's the case today. So let's go to the coding part. So here is a collab that I'm also going to attach in the video description. As of today, which is August 21st, 2024, like the Torch version is still 2.3 in the collab. I believe it will be updated to 2.4 very soon, and I actually want to use some of the 2.4 API. So in here, I manually install 2.4, but if by the time you watch this video, like the version is newer, like you don't need to do this. And then let's just do a bunch of imports. Right, so some warning is okay. And then just double check printer version. Yeah, it's like the PyTorch version 2.4 and the Torch XLA version is also 2.4. And as we discussed like last time, like in order to use SPMD, like you need to actually configure runtime to SPMD mode. So it's this XR that uses SPMD. So this Torch XLA experimental eager mode is something new, like in the 2.4. Pretty much like if you know PyTorch XLA previously, it was every torch operation you execute, it does not execute immediately. It was being accumulated as a graph node in the background. But it's actually non-intuitive for most people. So in the 2.4 release, I introduced the eager mode. So there is set it to true. We will see like how it's being used later. And then here is like the code I copied from the PyTorch XLA GitHub. It's called chain ResNet base. Pretty much like this is the code you need to chain a ResNet 50 on a single device. So let's just take a look. Like we set up batch size to be 128. We want to say we want to chain like 200 steps. Okay, what else? Okay, we set up a loader. And here, loader is just a fake loader. Like I didn't like for the sake of the simpleness, like I didn't actually use a real data loader. This data loader will just keep telling you the data is a bunch of torch.zeros. But nevertheless, we still initialize it with the correct batch size. And then we initialize the device, and then we wrap the loader with the PL, the MP device loader. This is actually sorry, this is something specific to the PyTorch XLA. Like, it's going to be more efficient because you're trying to do some prefetching and then like the multiple worker loading for you. It's also what we use to tell the compiler how do we want to shuttle the data, but it's not being used in a single device example. The rest of it is pretty standard. Like the model is the ResNet 50. Like optimizer is SGD, we use the cross entropy loss. Then here is another interesting part, like it's called compile step function. So we call Torch XLA.experimental.compile, like on the self.step function. So if you are familiar with the torch.compile, like this API is similar. I actually talk about this in release notes. You can check more detail. So pretty much this is kind of notification to the PyTorch XLA that I want to run this step function. I want to compile this step function instead of running this step function eagerly, because the compile will give you a lot of speed up and memory optimization. So let's take a look at the step function. So what is step function? This is pretty much like what we describe in here. So it was it's going to zero out the optimizer. It run the full path of the model. It run the loss function, do the backward and run optimizer. So this is what's supposed to happen in a single step. For the PyTorch XLA, we always want to just compile the step function. We always want to refactor the step function out and then just compile it. Yeah, and I think remaining in the model was pretty straightforward. Like we define how many steps is there, and we just like run the step function multiple times and then just do some logging. So this is for the single device training. So this one is actually what we want to talk about today, which is the I called it SPMD DDP. It's pretty much data parallel using the GSPMD. So let's see, what do we do here? So if you look at my previous video, like this part will be very familiar to you. Like we are initializing a 1D mesh. If you remember, it's pretty much is here. Like we define a mesh. So we define a mesh that's 1D, which is zeroth dimension is just a num device, and then we call this dimension data. So we are on a V4, a V2 8, so that 8 device. So this mesh shape is 8. And then in here, like this is the same as the previous part, initial chain loader. But when we're wrapping our loader with MP device loader, we're actually passing something called input sharding, which is a sharding spec. So if you remember, our input is 4D. It's a batch size times like the feature, and then it's the 2D image. So we tell the PyTorch XLA we want to shard the batch dimension, which is zeroth dimension, in the data mesh. Like if you remember, data is here. Data is corresponding number device. Pretty much means that we want to shard the input at the batch dimension. That's pretty much all it does. And every other dimension we just replicate. So yeah, like this is the code that if you want to take the profile, like you can enable this code. I also have a separate video for the how to take a profile and how to interpret a profile. So let's just get it running. And then like this TPU info is another CLI tool that's very useful. Like it's actually just recently published, and now it's like installed like in the in the Colab by default. It show you like the HBM usage of like all of the device. You can see here like we have like the 8 device in total, and this is V2 8. You see it's TPU V2 chip, and each device it has roughly like 8 gig of HBM, and now it's like 6.8 gig is being used. So it's actually pretty good. I think the previous we need to do some like graph compilation in the initial step. That's why we're kind of stuck for a while. But let me see, as the training actually getting started, like the duty cycle of the TPU also increased. It means like how much time it was being idle in the device, and now it's pretty high. It means that we are utilizing the device pretty well, and we almost max out of our HBM. It's usually a good sign that you use like the most of the device capability. So you will be training for a slightly longer, but you can see like the rate. I think the correct interpretation is like it's roughly processing like 3,000 image per second on all like in if you combining all of the 80 devices. Just want to remind you, we still only have like one process, like one Python process. It just within that process, it was able to use the SPMD to distribute the execution to all of the physical accelerator. And it ends. Like a loss is meaningless. I'm surprised it even go down because like both the label and the data are their fake data. They are all zeros. So yeah, that's everything I want to show you today. So as always, I'm going to post both the slide and the collab in the video description. If you have any question, please feel free to leave a comment or open a GitHub issue in the PyTorch XLA repository. And thank you for watching. See you.